Chapter 8, Introduction to Hypothesis Testing, Part 5, Directional Hypothesis Test. The standard hypothesis testing procedure is called a two-tailed or non-directional test because the critical region involves both tails to determine if the treatment increases or decreases the target behavior. So that's what we've been working with thus far. We've set alpha values and identified the critical region based on the z-score. And we were looking at values. Let's take alpha equal to 0.05. We know that the z is negative 1.96, positive 1.96. And again, we're looking at for values that fall on either side of the center, mu, which is a z-score equal to 0. And in other words, if our hypothesis simply says that we expect a change or difference, that change or difference can occur above the mean or below the mean. So back to the example where we were looking at the effects of the electric stimulation on math skills. Again, our hypothesis was very broad and general, and we didn't identify direction. Again, we simply said the electric brain stimulation will have an effect on mathematical skills. Again, noting that there is no direction identified. However, sometimes the researcher has a specific prediction about the direction of the treatment, and this is a good example that if the researcher is interested in the math skills, most likely they're interested in increasing the math skills, not decreasing them. So the electric stimulation may be hypothesized as a way of increasing those skills. And we'll talk more about why we would do a non-directional versus directional. So let's focus on what the directional hypothesis would look like for this particular example. So when a specific direction of the treatment effect can be predicted, it can be incorporated into the hypotheses. So the null, well, let's start with the research. And the reason I'm going to start with the research is because when you are working with directional hypotheses or tests, it's sometimes easier and less confusing to begin with the research hypothesis because that's the direction that you have on your mind. Once you verbalize the research hypothesis, then you can reverse the order, but I find it easier to verbalize because that's the interest that you are focused on. So, for example, the electric stimulation will increase math scores. Okay, and again, we had identified that the untreated population had a mu of 80. And so in the notation here would say that the treated population would be greater than, right? Because we expect it to increase. We expect it to be greater than 80. Notice how it's different than the notation we saw for the research hypothesis for non-directional. For the non-directional, we just said will not equal 80. Now we're specifying that we expect it to be greater than 80. So that notation will be reflected there once you verbalize your hypothesis. The null would say that the electric stimulation, and he would say the opposite, will decrease or have no effect on math scores. So again, now we're saying that it's going to do the opposite of what we're hypothesizing, but also say nothing will happen. So it always includes the will not happen, nothing will happen, nothing will change. So what does that look like in terms of the notation? So the mu treated, we're saying will be less than or equal to 80. So it always includes that equal. Remember when it was non-directional, it was just equal, right? The mu treated will equal 80. And now we're saying it's going to decrease or be equal to 80. So it's contradictory to the research hypothesis that says it will increase. So in a directional one-tailed hypothesis test, the researcher specifies either an increase or decrease. In this case, our example shows an increase in the population mean as a consequence of treatment. So again, that notation, we're hypothesizing the population mean after treatment, and the notation will reflect the change from what the original population, the original untreated population looks like. So some more specific information regarding the difference. So one-tailed test allows rejecting the null with relatively small difference, provided the difference is in the predicted direction. In other words, if we expect that the electric stimulation is going to increase, right, and we find a value over here, then we're in good shape. We get to reject the null. But let's say we find a value that's very statistically unlikely on the left side. Well, we would still, in this case, we wouldn't get to reject the null because it's not in the direction that we had hypothesized. Again, if we increase math scores, we expect our sample statistic to be in this tail. If it, even if it's a very rare sample statistic, it has less than a 5% chance of occurring. But if it's on the negative side, in terms of our z values, or less than the original mean, then we do not get to reject the null. So again, once we've identified the direction, it has to fall on that side that we predicted. A two-tailed test requires relatively large difference regardless of the direction of the the direction of the difference. So again, we're looking at both tails. And essentially what we're saying is that a one-tailed test is easier to pass simply because that proportion is larger. The tail, or the critical region, is slightly larger for an alpha at 5% for a one-tailed test opposed to alpha at 5% for a two-tailed test. And I'll show you a graph so that you can better understand that. But again, a one-tailed test is easier to pass because the parameters are a little more lenient in the sense that the critical region is slightly larger for a one-tailed test opposed to a two-tailed test. So in general, a two-tailed test should be used unless there's a strong justification for a directional prediction. Most research begins with a two-tailed hypothesis. We just expect a difference. Then if that difference is significant, we may revise and continue with a supplemental test with a directional hypothesis. And again, you have to have pretty good justification to begin at the one-tailed test because it's easier to pass. So we always want to be stringent in our research, make things more challenging so that we feel confident in our conclusions. In other words, they're rock solid. Our conclusions are rock solid, and they're rock solid because we were very conservative in the way that we drew these final conclusions. So this graph should help you better understand what we mean by a one-tailed test being slightly easier to pass. So up here we have the example relating to the mathematical test, the standardized test. The average score is 80. If it's a one-tailed test and we expect an increase in test scores after they've received the electric stimulation, then we're going to focus on the right-hand tail, which is shaded in blue, and the z-score, which I presented in a previous video. The critical region is set as z equal to 1.65. If you look in the unit normal table, z-score 1.65, in the tail you'll see 0.05 or 5%. That's where that value is coming from, and I've demonstrated how to locate that in a previous video. So we set the critical region, and again, now all we need to produce is a test statistic, a z-value of 1.66, 1.67, and by doing so, we get to reject the null hypothesis. Down here at the bottom, I've illustrated what it looks like for a non-directional test, again, alpha at 5%, and the critical region is set at a z-score of negative 9.6 and negative 1.96 and positive 1.96. And if we fall in those in the critical region, we get to reject. But notice that a z-score of 1.96 is further out in the tail, right? You would agree that 1.96 is further out than 1.65 because 1.65 is closer to 0 opposed to 1.96. And that's what I mean by a one-tailed test being a little easier to pass, because a two-tailed test at alpha 5%, we need a z-score of 1.97, 1.98, and so on and so forth for it to fall into the critical region. So again, visually, hopefully this affirms why it's best and more appropriate to begin with a two-tailed test and then continue with a supplemental test that includes a one-tailed test. So for the example of the electric stimulation, so we initially predict it will have an effect on math scores, and let's say it does, and the sample mean produces 89, and then we retest, revising our hypothesis, indicating that we expect an increase, and now we want to see if that increase is statistically significant. Obviously, if you pass it a two-tailed test, you would pass it also at a one-tailed test, but let's say we're now using a different sample of a different group of 25 individuals. Then we would revise the hypothesis so that it's directional, and now recognizing that at minimum we simply need a z-score of 1.65 positive to pass the test. And when I say pass the test, essentially what I mean is reject the null hypothesis, which is the objective of conducting a z-test or a hypothesis test. And we'll end with a quick learning check. A researcher is predicting that a treatment will decrease scores if the treatment is evaluated using a directional hypothesis test. Then the critical region for the test, and these options are, would be entirely on the right-hand tail of the distribution. So the right hand would be entirely on the left-hand tail of the distribution, would be divided equally between the two tails of the distribution, and then finally cannot be answered without knowing the value of alpha. Well, that's not true. We can understand which region of the distribution we're focused on, given this hypothesis that says we expect a decrease in scores. So we see that if we expect a decrease, obviously this is not appropriate. If we expect a decrease, this B looks good, but let's analyze C. C is looking at both tails, and again, since we said that we were specifying a decrease, it's directional. This would not be appropriate, and we would conclude that it would be concentrated in the left tail of the distribution because of the verbiage of we expect a decrease in scores. And that concludes this part of the lecture for Chapter 8. In the next part, we'll discuss measuring effect size, in particular Cohen's d, and then end the chapter with a discussion on statistical power.